Welcome to section 7.5, Sampling Distribution of the Sample Proportion. This topic is all about how sample proportions, like the percent of students in a class who drink coffee or the number of gamers who play Fortnite, vary from one sample to another. We're focusing on binary outcomes, successes or failures, yes or no, fan or not a fan. When we randomly sample a group from a larger population, we expect some variability in the results. The sampling distribution allows us to model that variability and use it to make inferences about the larger population. When we're working with sample proportions, we often want to approximate their distribution using a normal curve, but that only works under specific conditions. First, we assume we're taking a simple random sample. Second, both n times p and n times q must be greater than 5. Why? Because that ensures the sample is large enough for the normal model to accurately describe the sampling distribution. If we're looking at the proportion of Apex Legends players on campus, and we sample 100 students, we need to make sure there are at least 5 expected players and 5 expected non-players. Once that's true, we can treat the distribution of p-hat, our sample proportion, as roughly normal. That gives us access to powerful tools like z-scores and probability tables. Let's say we know from past studies that about 70% of students at our college drink coffee daily. We randomly sample 100 students and want to understand the distribution of the proportion who drink coffee. This isn't about whether a specific student drinks coffee. It's about how the proportion changes from one random sample to another. Even if the true population proportion is 70%, a random sample of 100 students might show 68% or 73% or maybe 75%. That variation is captured in the sampling distribution. We know the mean p equals 0.70 and calculate the standard deviation of p-hat as square root of p 0.7 times q 1 minus 0.7 or 0.3 divided by n, the 100. We get about 0.0458. This value tells us how much sample proportions are likely to deviate from the true 70% in repeated samples. Once we've established that our sample proportions are normally distributed, we can use z-scores to ask, how unusual is this sample? Let's walk through an example. Imagine someone claims that 80% of students are daily coffee drinkers. You sample 100 students and only 70% say yes. That's a decent gap, but is it statistically significant? So we calculate the z-score. The 0.7 we obtained minus 0.8 claimed divided by the p is 0.8 times q is 1 minus 0.8 or 0.2 divided by n 100. A z-score of negative 2.5 means this sample result is pretty far from what we'd expect under the 80% claim. It's more than 2 standard deviations below the mean, suggesting that the 80% claim might be exaggerated. Let's bring in pop culture. Suppose Pew Research estimates that 65% of adults in the US are Marvel fans. You want to test that among college students. You survey 200 students and 140 say they're fans. That's 70%. Is that difference big enough to challenge the 65% population proportion? So the mean is 0.65, our sample is 0.7, and our sample size is 200. We calculate the standard error of p-hat would be p 0.65 times q 1 minus 0.65 or 0.35 divided by n 200, about 0.0337. So the z is 0.7 minus the 0.65, right, divided by the standard error we just calculated. A z-score of 1.48 is not statistically significant. it falls within the expected range of variability. Remember, we're using about -2 to 2 as cutoff. So while your college might have slightly more Marvel fans, the difference is not strong enough to draw conclusions about the larger population. Here's one for you to solve: streaming habits. Suppose 62% of students nationally binge watch Netflix. In a random sample of 150 students at your campus, 100 say they binge watch. That's about 66.67%. Is this unusual? Your steps: calculate the standard deviation of p-hat and the corresponding z-score, then make a judgment. Go ahead and pause the video here and try it, and then resume when you are ready. Okay, here we go. Our p is 0.62. P-hat is 100 divided by 150, so 0.6667. Then the standard deviation of p-hat would be the square root of the p 0.62 times q 1 minus 0.62, or 0.38, over n, the 150. We get about 0.0396. Then z is 0.6667 minus 0.62 over 0.0396. Is that result statistically significant? What do you think? It's not more than 2. Let's recap. Sample proportions vary. That's randomness at work. The distribution of those proportions is approximately normal when n times p is greater than 5 and n times q is greater than 5. We calculate z-scores to determine how unusual a sample result is. Real-world applications? Everywhere. Coffee habits, superhero fandom, survey results, and yes, even Netflix binges. This is the kind of statistical reasoning that powers polling agencies, marketing departments, and academic research. Whether you're testing how many students actually read the syllabus or assessing the accuracy of a national claim, sampling distributions give you the tools to think critically with data.